Okay, welcome back. So, what we're going to start now is section number 1. Which is entitled Introduction and Mathematical Concepts. Okay, now physics is a quantitative science, meaning we're going to be using a lot of numbers in this course. So it's going to really help us to make sure that we understand what we mean when we use numbers to describe something. For example, in physics, when we say 2, what do we mean by that? Well, oddly enough, we need to describe what we're actually talking about. Usually in physics, when we say a number like 2, what we really mean is something that is about 2 or approximately 2. Now, sometimes we actually will mean exactly 2. Some quantity is exactly 2. But usually, and we'll talk about when we mean exactly 2 in a little while. But usually when we say something is 2, we really mean it's about 2 or approximately 2. If we're going to measure something, for example, maybe the length of a table or something like that, and we say that, oh, the length is 2 meters, what we mean is the length is about 2 meters or approximately 2 meters. In other words, what we mean is that the length of this thing is closer to being 2 meters than it is to 3 meters. Hopefully, if the length actually were closer to 3 meters, we would have said 3 meters rather than 2 meters. So we mean that the length is closer to 2 than it is to 3, if it's a precise measurement. Hopefully we're precise as possible. So let's say it's closer to 2 than it is to 3. Likewise, the measurement is closer to 2 than it is to 1. Likewise, if it was closer to 1 meter long, we would have said the table is 1 meter long. So very approximately, we'll say something like the measurement is, say, closer to 2 than it is to 1, closer to 2 than it is to 3. In other words, about, say, 2 plus or minus 0.5, roughly speaking. If it was more than 0.5, larger than 2, hopefully that's closer to 3. Hopefully we would have said, oh, well, that's 3 meters. If it's more than 0.5 less than 2, that would have been closer to 1. So hopefully we would have said, oh, that's 1 meter long. So roughly speaking, when we say 2, we mean about 2, and we're talking about something that is approximately somewhere in between 2 plus 0.5 or 2 minus 0.5. In other words, 2 plus or minus 0.5. So let's imagine we're talking about a distance, maybe the distance, say, from where we are now to some other place. And rather than 2, let's say 2,000. Let's imagine I say that the distance from here to some place is 2,000 meters. Now, what's the difference between saying the distance is 2,000 meters or 2,100 meters or 2,130 meters or 2,132 meters? Well, by saying, let's say, so here, say if we said it was 2,000 meters, remember what we're talking about then is something that's closer to 2,000 than it is to 3,000 or 1,000. So we mean really something like 2,000, say maybe plus or minus 500 meters. While here, if we say 2,100, we mean something that's closer to 2,100 than it is to 2,200 or just 2,000. So we mean a number that's maybe within only 50 meters. If we say 2,130, we're talking about something that's closer to 2,130 than it is to 2,140 or 2,120. So we're saying maybe something within, say, 5 meters. And like we were talking about before, 2,132, that would be, say, closer to that than 2,133 or 2,131. So we're saying maybe plus or minus 0.5 meters. So we will describe these different numbers in terms of how precise they are. So this is more precise than this number. This one is more precise than this one. This is more precise than this one. In other words, the error, so to speak, associated with the values is smaller as we move down the list. Now, we'll talk about that very simply in terms of the number of significant figures how many significant figures numbers have. And we will use that to kind of describe the precision that values have. So how do we determine how many significant figures a number has? Well, if the number does not have any zeros, it's pretty easy. So for example, if we have a number like 4,367, all we have to do is count up the digits, and that's how many significant figures there are. Excuse me. So 4, 3, 6, 7. That number has 4 significant figures, or I'll say sig figs for short. Sometimes I'll just write this as SF, sig figs, significant figures. So that number has 4 significant figures. As long as there are no zeros, all we have to do is count them up. And it doesn't matter if there's a decimal point. So for example, 23.86478, and I'm writing these numbers, specifically these numbers, because they are the ones in the lecture notes. If you have access to the lecture notes, you can see them there. So in this case, how many sig figs does this number have? Well, we just count them up. 1, 2, 3, 4, 5, 6, 7. So that has 7 sig figs. Now, if there is a 0 in the number, that makes it a little bit more complicated to determine how many sig figs there are. But there are 3 rules for counting zeros as whether they are significant figures or not. So let's take a look at those one at a time. Okay, rules for counting zeros. Rule number 1. Zeros to the left of all non-zero digits are never significant. So let's look at some examples of that. 0.0023. These are the non-zero digits. These are the zeros to the left of the non-zero digits. They are never significant. So how many sig figs does this number have? Not significant. 1, 2. 2 significant figures. 0.0000000367. All of these zeros are to the left of the non-zero digits, so none of these are significant. 1, 2, 3. 3 sig figs. Okay? 0.000004. None of them, still only 1 sig fig. There we go. So keep in mind, zeros to the left of all non-zero digits are never significant. Rule number 2. Zeros between non-zero digits are always significant. These are sometimes referred to as sandwiched zeros. So let's look at some examples of this. 104. Now that 0 is in between the non-zero digits, and so it is significant. So 104, that has 3 significant figures. And it doesn't matter if there is a decimal point. 2.30046. We've got non-zero digits, non-zero digits. These zeros are in between the non-zero digits, and so they are significant. So we have 1, 2, 3, 4, 5, 6 sig figs. 5050.003. This 0 is in between non-zero digits. These zeros are in between non-zero digits, and so they are all significant. 1, 2, 3, 4, 5, 6, 7. Okay, let's look at rule number 3. And rule number 3, zeros to the right of all non-zero digits are significant only if there is a decimal point present. So, to the right of non-zero digits, only significant if there is a decimal point. So let's look at some examples of this. Okay, some examples of rule number 3. 1,300, so this is kind of similar to the number we were talking about before. Here are zeros to the right of the non-zero digits, but there is no decimal point present, no decimal point written in the number, so those are not significant, so we have two significant figures. If we were to write this number as 1,300 but include the decimal point, then that makes those significant, and we have 1, 2, 3, 4 significant figures. If we were to include even more zeros after the decimal point, then those zeros are still to the right of the non-zero digits. The decimal point makes them all significant. 1, 2, 3, 4, 5, 6. 6 sig figs. Okay? Decimal point makes the zeros to the right of the non-zero digits significant, and so 1, 2, 3, 4, 5, 5 sig figs. 39.00. Again, the decimal point makes the zeros significant. 1, 2, 3, 4. No decimal point. So the 0 is not significant. That only has 1. However, 60.000, the decimal point makes the 0 significant. 1, 2, 3, 4, 5. Okay, there we go. Now, in general, obviously, a number might you might need to use different rules to determine how many significant figures a number has. So, for example, 1.45, well, there are no zeros, so that's pretty easy. 1, 2, 3. 1.005, well, those are sandwiched zeros, so 1, 2, 3, 4. 0.000450. Those zeros are to the left of the non-zero digits and are not significant. This 0 is to the right. There is a decimal point, so it is significant. 1, 2, 3. 405.060. Well, those zeros are in between non-zero digits. That 0 is to the right. There is a decimal point, so it is significant. 1, 2, 3, 4, 5, 6. So, sometimes you've got to make sure to keep, well, all the time, you should make sure to keep all those rules in mind because you might need any of them in determining the total number of significant figures. Now, in physics, we are also going to be dealing with some very large and very small numbers. And so there is a way of writing very, very large numbers and very, very small numbers that makes it a little bit easier for us to deal with them sometimes. And that is called scientific notation. For example, let's imagine we've got some large number like 167,000. So that would be like 1,670,000. Sometimes if you're writing this number, it might be very easy to miscount the number of zeros, and you might put an extra 0 or leave off a 0 or something like that. So there's a way of writing it to make sure you know exactly the size without having to worry about counting the zeros all the time. Now, to write this in scientific notation, we write the first non-zero digit on the left, which in this case will be a 1. We follow that with a decimal point. And then after the decimal point, all of the other significant digits. Now, in this case, we have 6, 7. Now, 1.67 is obviously not the same as 1,670,000, so we need to make this bigger to make it the same size as this. To do that, we multiply by a power of 10, which has the effect of moving the decimal point some number of places. And the number of places, we make the power of 10. So if we were to multiply by just 10, that would move it one place. If we multiplied by 10 to the 2, in other words, 10 to the second power, 10 squared, that would move it 2 places. 10 to the 3, 3 places. Well, we need to move it from 1.67, we need to move it 1, 2, 3, 4, 5, 6 places. So we say that this is 1.67 times 10 to the 6th. And then that number is the same size as that number. And this is then what we say in scientific notation form. That number is written in scientific notation. For example, we could also write very small numbers in scientific notation. For example, let's say 0.00053. Again, we write the first non-zero digit on the left, which in this case would be 5. Follow it with a decimal point, and then all of the significant figures afterwards to the right, which would be in this case 3. And then we multiply again by a power of 10, because obviously 5.3 is not the same as 0.0053. But in this case, we need to make this smaller to be the same size as 0.00053. So we need to move the decimal point to the left. And in this case, we need to move it how many places? Well, from here, 5.3, we need to move it 1, 2, 3, 4 places to get it back to where it should be in the original number. So we have to multiply by 10 to the negative 4. 1, 2, 3, 4. Yeah, negative 4. So 5.3 times 10 to the negative 4 is the same as 0.00053. It's a very, very general rule of thumb. Try to keep in mind that positive exponents of 10 are big numbers, negative exponents of 10 are small numbers. So positive exponents, big, negative exponents, small. Just try to keep that in mind. We'll come back to that a lot. Okay, now, how do we use these ideas of, sorry, one more point. The one thing that's very helpful about scientific notation, it allows us to write numbers with the correct number of significant figures, even if it would be difficult to write in this form. So, for example, let's imagine we want to write this number 1,670,000, but for some reason we happen to know that it actually has 5 significant figures. In other words, these zeros here, let's imagine we really do know that those are zeros, they are significant. How can we write this with 5 significant figures? Well, if we write it in scientific notation, we could write 1.6700 times 10 to the 6th. By putting these extra zeros over here, then we know 1.6700, that has 5 significant figures. While if we write it in this form, this only has 3 significant figures. So, by writing a number in scientific notation, we can write as many significant figures as we want for the appropriate number for the original number, for the appropriate number of significant figures for the original number. So perhaps this number came about as the result of a calculation or something like that, and we really want to make sure that that has 5 significant figures. If we write it in scientific notation, we can always be sure to emphasize how many sig figs it has. There's some notation kind of underlying significant figures or something like that. I think this is just a neater way of doing that, so we'll do it this way. We'll write it in scientific notation if ever necessary to emphasize how many sig figs it has. Okay, now how do we use these things? Why do we worry about these kinds of things?